So our next topic is parallel resonance, and this is also a dual of a series resonance circuit. So let me draw a parallel circuit here. So this is our parallel RLC circuit where incoming current is I and this is IR. This is I1, which is equal to IL plus IC. Okay, so this is R, this is L, this is C. Now the voltage across the parallel circuit is same, so we'll keep the voltage at reference axis, that is VR, and the current in this path will be I, okay, which is equal to V by R, because in resistance current and voltage is in same phase. Now IC will lead voltage by 90 degree. This will be V into V by XC, which can be written as V into XC is 1 by omega C. So this can be written as V into omega C, or we can write this as V into YC. Okay. Similarly, IL will be in lagging nature. It will lag voltage by 90 degree, and this is V divided by XL. So we can write this as V by XL is omega L, or we can write this as V into YL. Okay, this is admittance value. Now with the help of this phasor diagram, we can write the admittance by the current source Y is YR plus YL plus YC. Okay, or you can also write here V into YR. Okay. So YR can be represented as 1 by R plus YC. YC is represented as omega C, right? YC is omega C. And you can see this YC is leading by 90 degree. So how we represent this? We represent this by J. Now YL plus YL. So YL is actually 1 by omega L. Okay, this is 1 by omega L, and YL is lagging by minus 90 degree. Okay, sorry, lagging by 90 degree. So how to represent this lagging term? We can represent this by minus lagging by 90 degree. So we use term minus J. Okay. Now what is 1 by R? 1 by R is conductance plus J. This is susceptance. Okay, omega C minus 1 by omega L. So I represent this by G plus J B. Okay, so G is conductance and B is susceptance. Now in series circuit at resonance, reactance was equal to 0. The total reactance was equal to 0. That is XL minus XC should be equal to 0. Okay. In parallel resonance circuit, your susceptance B should be equal to 0. So what it means? That omega C minus 1 by omega L should be equal to 0. So at resonance omega C, or we write first B should be equal to 0. That is omega C minus 1 by omega L should be equal to 0, or omega is equal to 1 by under root of LC. Okay, because this will become omega square, and omega square is equal to 1 by under root of LC. Okay, because if you move this to the right side and use cross multiplication, you will get omega square, and omega will be equal to 1 by under root LC. Now this we got 1 by under root LC radian per second. Now at resonance your current IC, that should be equal to minus IL, because as you can see in this phasor diagram, 1 by XC should be equal to 1 by XL, right? This is XC and this is XL, right? So 1 by XC should be equal to 1 by XL, and V is common, so we can write this as IC should be equal to inverse of minus IL. Okay, now current I1, this current, okay, current I1 will be equal to IC plus IL, okay, and if IC is equal to minus IL, this current will be equal to 0, and if this current will be equal to 0, there will be only IR in the circuit, okay, or you can tell I is equal to IR, I will be equal to IR, okay. So at resonance your current I will become equal to IR and circuit will behave exactly as resistive circuit. Now initially what was the voltage across this? Okay, so the voltage across this will be equal to, so the voltage will be equal to I divided by admittance, okay, which is equal to I divided by G plus JB. So if B will be equal to 0, okay, if B is equal to 0, the overall value of this will decrease, and if this value decrease, value of voltage will reach to the maximum value. So at resonance you will get the maximum voltage Vm, that is equal to I divided by G, or we can write I into R, because G is 1 by R. Okay, now what is the formula of power? Maximum power. So at maximum voltage you will get maximum power. So this will be equal to Vm square divided by R. Now at half power frequency, that is Pm by 2, we can write this equation as Vm by root 2 square into 1 by R. It means we will get half power at Vm by root 2. Okay, so the frequency at which we will get this value is called half power frequency. Okay, let's understand this by plotting a graph. So this is the value, this is the frequency omega r at which we will get maximum value of current, maximum value of voltage. This is voltage V and this is frequency omega. So at this point you got maximum voltage, that is Vm, which is equal to I into R, or I by G. This is the frequency at which we will get half power. This is omega 1 and this is omega 2. So at this frequency we got half power. It means the voltage at this frequency should be equal to Vm by root 2. So this is half power frequency, omega 1 and omega 2 is half power frequency, and omega r is resonance frequency. Now what will be the quality factor? Quality factor is 2 pi into maximum energy stored divided by energy dissipated. So here we can take C as a energy storage element. So we can write this as half CV square, and energy dissipated element is R, right? So this will be half into what is energy dissipation, that is I square R, or we can write this as V square divided by R over a period. So we need to multiply this with T. So actually quality factor mean it is a perimeter of an oscillatory system. Like in this, how much energy is stored in every cycle, how much energy is stored by the storing element, and how much energy is dissipated by the element. Okay, so that is called power factor. That is called quality factor. Okay, it's a perimeter of an oscillatory system or device. Okay, and I multiplied here by 1 by 2 because we have two storage element, right? That is L, and energy storage element, that is L and C. So in half cycle, resistance dissipate energy of capacitor, and in half cycle resistance dissipate energy of inductor. So this will give you 2 pi F CR, which is equal to omega naught CR. Okay, or we write resonance frequency omega R. Since omega RC should be equal to 1 by omega L, so we can write this formula as R by omega R L. So Q should be equal to either omega R CR or R by omega R L.